This is Amy Wang, and in this video, I will be conducting a lab that tests out Newton's second law with constant velocity. Newton's second law states that V final equals F net divided by m times delta t plus V initial. However, because we are testing the law using constant velocity, F net should equal 0, rendering this entire part of the equation to also equal 0, making V final equal V initial, giving us constant velocity. To do this lab, we will be collecting data from the observed motion of a toy car going in the same speed in the same direction. I recorded this video of a car rolling across a flat surface and put it into this system called Tracker. I will only be observing 22 frames of this video because it is where the car seemed to be rolling at the most constant speed. At each frame, a point mass, or these red dots, was recorded, giving the position of the car of each frame. From this data collected here, this graph can be seen. Before we talk about this graph though, let's look at the calibration stick and the axis. So this calibration stick gives the length of the toy car, which I measured to be 0.083 meters. The axis here has positive y pointing up and positive x pointing right. However, the orientation of this axis does not really matter. It just makes it easier for us to read our data. Time, velocity, net force does not change no matter which way the axis is facing. So now back to the graph. It seems almost linear. This tells me that I have near constant velocity. However, it is not completely linear, which could be caused by different forces, such as air resistance, friction, gravity, or perhaps just human error in calculating the point mass wrong. So let's say we wanted to test out the same constant velocity but with no errors. This is when we would use a computational model. In this case, we will be using this Python code in vidle. To start this code, we will need the initial conditions that we received from our tracker data. Here we have our initial time, which we chose when to start our clock, which was 0 seconds. From this, we have the initial position that we also got from our tracker data and the initial velocity, solved using this equation here. So now we go down to our while loop. We chose time equals less than 0.733 seconds because that was the time of our last observation. Here we are setting F net equal to 0, meaning constant velocity, as I said earlier, and these two equations of velocity gotten from Newton's second law and position will give us the position at each time interval. So let's run the module and check out our constant velocity graph. So as can be seen, the graph is perfectly linear here, and the ball is moving in the same direction as our car was moving. Now let's take this data from the computational model and compare it with our observed data. We do this by taking the data points of our observed model and the data points of our computational model and putting it into Excel and creating a scatter plot graph. As seen in this graph, the observed data, which is the red, is fairly close to the model, which is the blue. This proves that Newton's second law of motion is true and trustworthy. There are some derivations though, and as stated earlier, it could be caused by other forces such as gravity, air resistance, friction, and human error. However, if these forces did not exist and no human error had been made, the observation data most likely would have been exactly the same as the computational model.